Hey, welcome everybody to today's live stream presentation. We're going to be talking about an introduction to disaggregated serving in TensorRT-LLM. And for that topic, we have a team of software engineers from NVIDIA, Patrice, Xianxie, and Xiaowei. You can join us in the conversation after the live stream at github.com/NVIDIA/TensorRT-LLM. We can also be found on Discord via discord.gg/NVIDIA developer, and we'd love to have you be a part of the conversation there as well. And finally, if you want to ping us directly, we always respond quickly to community@nvidia.com, and we'd love to hear what you have to say. And with that, why don't we kick it off?
Thank you, Ethan. Thank you all for attending this talk about disaggregated serving with TensorRT-LLM. My name is Patrice, and I will be presenting with my colleagues Xiaowei and Chengji. Here's the agenda for the live stream. So we'll talk about the motivation for doing disaggregated serving versus regular in-flight batching without disaggregation. Then we will talk about the different ways that you can do disaggregated serving with TensorRT-LLM. Xiaowei will talk about the KV cache exchange process, which is a key component in disaggregated serving. And Changji will then present some performance studies we have done with disaggregated serving on some key models. So to better understand why we want to do disaggregated serving, it's helpful to look at the LLM inference process without disaggregation. And the figure on the left is showing that process. As you probably know, when processing an LLM inference request, there are two main phases. The context phase, this is where we would compute the KV cache blocks associated with the prompt tokens, and the generation phase, where we generate tokens one by one in an auto-regressive fashion. So on the figure on the left, we see like the process of the LLM inference process, where we have 6 incoming requests. And in this case, we assume that we can only process 2 requests at the time. So our maximum batch size is 2. And the darker color, they represent the context phase, while the lighter colors, they represent the generation phase. So what we see is that first, we would start by processing the first 2 requests. We would do the context phase and then start generating tokens for those 2 requests. At some point, the second request terminates after 4 generated tokens. And with in-flight batching, we would then schedule a new request, in this case, the third request that is ready to be executed. Now, what you can see from this figure is that at this particular iteration, there is interference between the first request that's still in the generation phase and the third request, which is now in the context phase. So the token-to-token latency for that first request at that particular iteration increases because there is interference between the requests that are in the context phase and the requests that are in the generation phase. So the main idea is that with disaggregation, you actually do the context phase and the generation phase on separate pools of GPUs. And by doing that, you no longer have interference between requests that are in context and generation phases. You're still doing in-flight batching on the generation and the context instances, but now you're doing them on separate pools of GPUs. Another key advantage of doing disaggregation is that now you can configure your context and generation instances completely like independently. So you can choose different parallel mappings, TP, EP, PP, sequence parallelism for your context and generation phases differently. You can also pick different GPU types. You can configure your software differently for context and generation. So you no longer, with disaggregation, you no longer have to trade off like one metric, let's say time to first token and time per output token. You can tune those separately. Disaggregation is not a silver bullet. There are some caveats. One one thing that you need to do when you do disaggregation is transfer KV cache blocks from the context instances to the generation instances. There's a cost associated with that. Also, you need to make sure that your context and gen instances are rate matched, meaning that the aggregate throughput of your context instances must match the aggregate throughput of your generation instances. Otherwise, your GPUs will be idle on either your context or generation instances. And also, as we'll see in a couple of slides, disaggregation doesn't always help. There are some traffic patterns, some ISL, OSL combinations where the gain from disaggregation is fairly limited. So how do we compare performance of disaggregated serving versus regular IFB without disaggregated serving? Typically, we would create a plot that looks like this, where we plot on the y-axis the throughput of our LLM inference deployment. So that's measured in terms of tokens per second per GPU. And on the x-axis, the inverse of user perceived latency, which is tokens per second per user. Like obviously, you can configure your LLM inference deployment in different ways. So each individual point on this chart corresponds to a different configuration. For example, different TP, PP mappings for your context gen instances, different ratios of context to gen instances, even different concurrency. And to draw that Pareto curve, you would simply pick at a given latency what is the best throughput that you can achieve. This particular figure was obtained using a high fidelity simulator that we have at NVIDIA. And it shows for Llama 70B for input sequence length of 2000, output sequence length of 128, that with disaggregation, the blue curve, you can get a significant improvement in throughput at different latency thresholds. As I alluded to earlier, disaggregation, the gain that you can get from disaggregation will depend on your traffic pattern. Here, using that simulator, we looked at what that Pareto curve looks like for different ISL, OSL combinations. And we can see in the first figure, for the case that we showed earlier, there's a significant gain that can be expected from disaggregation. But for a generation-heavy case, like the third figure, the gain with disaggregation is fairly limited. And if you want to have more details about the other factors that can impact disaggregation performance, I invite you to take a look at that paper that was published by NVIDIA a few months ago. So before we move on to the next section, I guess we could pause here and like if there are any questions, we might be able to take a few questions.
So, Patrice, it looks like people are following along quite well. So we don't have any questions yet. But as we continue, please feel free to ask.
Sounds good. So we can move on to this section, which is about how you do disaggregated serving with TensorRT-LLM. There are essentially three main approaches to do disaggregated serving with TensorRT-LLM. The first one involves using the Triton inference server. The second one involves using TRT-LLM serve, which is a command line tool that we provide with TensorRT-LLM. And the final one, which is the approach we recommend for large-scale like production deployments, is to use Dynamo, which is a data center scale LLM inference framework that's developed at NVIDIA. For both the Triton inference server and the TRT-LLM serve approaches, the workflow looks like what's shown on this figure. In both cases, we have an orchestrator that is responsible for receiving requests from client and sending responses back to the client. Then that orchestrator will forward that request to a context instance, which will then process the prompt, compute the KV cache blocks associated with the prompt tokens, return the first generated token and also metadata about the context instance that processed this request. This metadata, along with the first generated token, is passed to the generation instance. And using that metadata, the generation instance can establish communication with the context instance to exchange the KV cache blocks. Once the KV cache blocks have been sent from the context instance to the generation instance can start generating tokens and return them to the orchestrator. When using the Triton inference server, we use what's called in Triton an ensemble model, which is essentially a pipeline of models. And for disaggregated serving, we have 3 models in our pipeline: the pre-processor that's responsible for tokenizing the input prompt. We have the disaggregated serving model instance, which plays the role of the orchestrator that we talked about earlier, and finally the post-processor. That disaggregated serving model instance is then responsible for sending the request to the context instances and to the generation instance. In this particular example, we show deployment with 4 context instances and 1 generation instance. The Triton inference server approach is no longer being actively worked on. It has some limitations compared to the other 2 approaches. It uses the TensorRT-LLM executor API, and that API only supports the TensorRT backend. So TensorRT-LLM has a TensorRT and a PyTorch backend. With the Triton inference server, right now you can only use the TensorRT backend. It's a little bit harder to set up than TRT-LLM serve and Dynamo. And also we don't support dynamic scaling of instances when using the Triton inference server approach. The second way to do disaggregated serving with TensorRT-LLM is to use TRT-LLM serve. TRT-LLM serve is a command line utility that allows you to easily stand up an OpenAI compatible server. So what you can do with TRT-LLM serve for disaggregated serving is to create 1 server instance per context instance and then 1 server per generation instance. In this example, we could have 4 context servers, 3 generation servers. And finally, you could use TRT-LLM serve to essentially launch this disaggregated server, which plays the role of the orchestrator. You can launch it using the TRT-LLM serve disaggregated subcommand. And that proxy server, again, is taking requests from the client, returning them to the client, but also routing those requests to the context instances, the generation instances. And we support, in that disaggregated server, different load balancing strategies. So different strategies to pick to which context server, to which generation server to route the request to. We support load balancing of request tokens. We also have a KV cache aware router, which will pick the context or the generation server that is most likely to have KV cache blocks associated with the given prompt. And these are the commands that you would use to set up a disaggregated serving deployment with TRT-LLM serve. In this example, we launch 2 context servers and 1 generation server on different ports on the current host. And we would launch the proxy server as follows, where you would list in your configuration file the URLs of the context servers and the generation servers. Compared to the Triton inference server approach, it's much easier to set up. TRT-LLM serve is quite user-friendly. You can easily pass all your parameters in the command line itself or in that YAML file. We support both the PyTorch and the TensorRT backends. Under the hood, we use the LLM API, which is all in Python. So for developers who would like to contribute to changing TRT-LLM serve or that LLM API, it's easier. But one thing is that TRT-LLM serve was really meant to be kind of a demonstration of how to do disaggregated serving with TensorRT-LLM, and it's not the recommended way to do to have a large-scale deployment with TensorRT-LLM. For that, we recommend that people take a look at Dynamo. You can have a look at the documentation at this website. Dynamo is really a data center scale LLM inference framework. It has product level support. Dynamo supports different LLM inference engines, with TRT-LLM being one of them, but it supports also VLM and SGLang. And it has some nice features, such as the KV cache aware router we talked about earlier, but also it has the option to have decoupled, so separate pre and post processor workers, which can be helpful in the case where your concurrency is quite high and where tokenization, detokenization can become a bottleneck. It has other tools also to simplify the deployment and management of Dynamo inference graph, like to deploy them on Kubernetes clusters. It has built-in monitoring and metrics. And so we strongly recommend that you take a look. Okay, so that concludes the section about like disaggregated serving with TensorRT-LLM. I guess we could also pause here and take any questions if there are any.
We do have some this time, Patrice. So first one is from Swag Junk. You mentioned costs or drawbacks. Can you clarify?
Yes. So I guess I imagine that you're referring to some of the caveats when doing disaggregated serving. So as I mentioned, you need to, when you do disaggregation, the KV cache blocks associated with the prompt tokens are computed on the context instances. Those KV cache blocks, they need to be transferred to the generation instances. There's a communication cost associated with that. With disaggregation, you need to rate match your context and generation instances. And also, like in some cases, as I've shown, depending on the traffic pattern, like depending on your ISL, OSL combinations, disaggregation might not always help. Hopefully that answers the question.
Yeah, appreciate that. And then we have two more quick questions from Hangan G. The first is, what are the specs of the instances and disaggregation servers? Do we have that?
I guess it's not clear if that question is for the charts where we show those Pareto curves. So along that Pareto curve, right, the configuration could be different. So like the configuration, so TP-PP mapping for a point like here on this line might be completely different than the optimal configuration for a point in the lower right corner of this curve. For super low latency, you probably want to have like a low concurrency batch size of 1. For best throughput in the upper left corner, like running with a larger batch size typically utilizes the GPUs more efficiently. So the optimal configuration is not shown, and I don't have them, but it will vary along this curve.
Okay. And then the last question is, what are the references to the paper that you made? Do we have access to that paper that we can share, like a link?
Yes. So the link is shown at the bottom of the screen. We can probably share it in the chat as well. But if you do a search for like Beyond Buzz pragmatic take on inference disaggregation, you should be able to easily find it. That's available on the NVIDIA website.
Great. That's really helpful. Okay. So if we can move to the next piece of the presentation.
Yes, and so for this part, Xiaowei will be presenting and talking about the KV cache exchange process.
Hi everyone, let me walk you through the key points of the KV cache transmission. Now in TRT-LLM, The KV cache exchange is designed as a separate module. It's independent from both the KV cache manager and the communication libraries. This design allows it to handle sending and receiving KV cache efficiently. It also helps free up memory quickly and converts the cache layout during the exchange process. Currently, TRT-LLM supports all major communication protocols, including MPI, UCX, and NIXO. For actual data transfer, it uses RDMA or NVLink. On top of that, we are building a dynamic scaling feature. This means nodes can join or leave on the fly, which gives customers the flexibility to adjust the load based on traffic. They can also switch between context and generation roles as needed. The KV cache transmission is designed to run efficiently in parallel with computation and across multiple transmissions. For example, while one request is sending or receiving KV cache, other requests can continue computing without waiting. Even within the same request, KV cache transfers between different nodes can happen simultaneously. Plus, transmissions from different requests can also run concurrently. To reduce latency, TRT-LLM now uses direct device-to-device memory transfers for KV cache transmission. It also supports using different parallel strategies for the context and the generation phases. In those cases, we need to carefully coordinate how KV cache blocks are mapped. If you look at the diagram on the left, you will see an example where context uses TP2 and generation uses PP2. Due to time constraints, I won't go into the details layout here, but if you are interested, feel free to check out the source code for more insights. Thank you, everyone.
Oh, Ethan, you're on mute.
Thank you. Are there any questions for that last part of the presentation? If not, we can move on to the next part of the presentation.
Okay. Thanks. And this is Xianjie from TRT-LLM team, and I'm going to introduce some of our performance stats. Let me begin with an please, next slide. Let me begin with an overview of our disaggregation benchmarking methodology, followed by the measured performance results for DeepSeek R1 and Qwen 3. As we all know, creating a disaggregated product curve is a challenge because we need to explore a vast configuration space and including different parallelism combinations and a lot of tuned parameters, something like max batch size, max number of tokens, MOE backend or reduce strategy, MTP, and so on. And we also need to explore a large number of context and generation instance combinations. And testing every possible combination takes a lot of time and resource. So we built a two-step approach to efficiently find the best configuration. The two-step approach are request rate matching stage and end-to-end benchmarking stage. In the request rate matching stage, first, we measure the context only and generate only performance separately from the given dataset across all of the possible configurations and concurrencies. And based on the context-only results, we will select the best context configurations that not only satisfy the TTFT constraint, but also will achieve max context tokens per second per GPU. And using this best context configuration, we then apply the request rate matching methodology to compute the token per second per user and the token per second per GPU for each generation configurations and concurrencies, and which allow us to produce the final Pareto curve. And based on the then based on the hardware resource constraint, we will determine the best context generation ratio, and then process the ratio to the and configurations to the end-to-end measurement, and then in the end-to-end benchmarking stage, we will use TRT-LLM serve with the selected context and generation ratio and configurations from the request rate matching results, then obtain the actual performance numbers for disaggregated servings for the given dataset. And using this methodology, we measured the disaggregated serving performance for DeepSeek R1 and Qwen 3. I will present the results in the next two slides. And this slides shows what we have measured for the dataset at K to ISL at K, OSL 256 on DeepSeek R1. The left figure one is based on Gen 4 GPUs, which means we set the GPU number of aggregation to 4, and also set the Gen instance GPU numbers of disaggregation to 4. The right figures show the results for Gen 8 GPUs. We included 3 curves into the graph. The top curves, which represent the request rate matching Pareto curve, and then the other two are the real disaggregated end-to-end curve and the real aggregation end-to-end curve. From these figures, we can see compared to aggregation, disaggregated end-to-end can achieve up to 1.73 speed up in the Gen 4 and the same token per second per user, and up to 2 times speed up in Gen 8. The reason why Gen 8 has bigger speed up is still using the DEP4 for context instance. Context DEP4 is much efficient than context DEP8. However, we also see there is still performance gap between disaggregated end-to-end and disaggregated request rate match curve. There are 2 potential reasons. The first one is the disaggregated request rate match curves allow the decimal values for context generation ratio, and the other reason is the QV cache transfer. The other reason is there may be other overhead, such as QV cache transfer and other Python overhead. Besides these 2 reasons, maybe there are still some other overheads we are still doing the further investigations. And next, please. And this slide presents our measurements on the ISL HK OSL 1K dataset within a single GB200 and NVL 72 rank. We also include the three curves into the graph. From the figures, we can see the max speed up of disaggregated versus aggregated is about 6.11 times. The speed up is higher than the DeepSeek hour results shown in the previous slides. The reason for this is Qwen 3. This is a model from Qwen 3 235 billion. It has smaller size than DeepSeek hour, which enabling us to run the Qwen 3 IP4 models onto a single GB200 card. And this allows us to explore more context and generation configurations. And as we can see, the highest speed up occurs at the point 4 context TP1 and 15 generation TP4. Furthermore, the performance gap between the disaggregated end-to-end and disaggregated request rate match curve is also smaller. I think the reason is also due to we could sweep more possible combinations of context gen ratios within NVL 72. Okay.
We do have a few additional questions. So first and foremost, if we have any questions from the audience specifically for Xianjie, I strongly recommend you add them here because we'll have some time to speak to those. In the meantime, we have 3 questions that we'd like to bring up here from YouTube. Is the data movement GPU to GPU data movement? Is this data movement?
Yes, right now our KV cache is transferred directly between devices to reduce latency. We've seen that others are using host and storage setups, and we are also discussing and trying those internally. Thanks.
Great, thank you. Okay, next question also from YouTube. Do these KV cache copy data between context instances to generation instance? If there's an issue such as latency, could you let us know? If not, is NVLink fast enough to just ignore?
Yes, after the context instance sends the KV cache to the generation instance, it tries to offload it quickly to free up device memory. This does affect latency a bit, but only the TTFT part. We are working on reducing that overhead. Thanks.
Great. And then finally, one more question here from Gal from YouTube. He wants to know, the idea is to use memorization KV cache with coroutine style scheduling, so multiple requests advance in lockstep, processing tokens in batches of n across k GPUs like threads. Is that right?
The main idea of disaggregated serving isn't to run multiple requests at the same time. It's more about separating the context and generation stages so they can use different configs and run on different types of devices. The kind of parallel processing you mentioned can be done using other features like in-flight batching. Thanks.
Okay, and looks like we have one more question from Claudius from YouTube. And they would like to know, are there potential bottlenecks in transferring KV cache blocks between GPUs?
We haven't seen bottleneck in transferring the KV cache between GPUs now. And the bottleneck is mainly in the in different workloads that fit in the context stages and generation stages.
Great, thank you. And actually, one last one, it looks like, from YouTube. Wyming would like to know, for the inference results, were you using FP4 or FP6?
Yes, all of our benchmark results are using the NVFP4 model.
Okay, that's really helpful to know. Thank you, gentlemen. That looks like that wraps up the questions. So once more, I would like to thank our community for joining us in this conversation, and also thank the engineers here at NVIDIA for taking the time to provide this information and answer all of the community's questions. Thanks, fellas, and until next time, we'll catch up with you later.
Thank you.
Thank you.
Thank you.